Welcome back to AI.Code.Cast. Today we're diving deep into a classic coding challenge.
Oh, yeah.
It's all about strings and palindromes.
Okay.
The shortest palindrome problem.
Ah, yes. This one is deceptively simple,
Yeah,
but has some surprising twists and turns when it comes to finding the most efficient solution.
exactly. So for our listeners,
Right.
imagine you're given any string of letters.
Uh-huh.
The goal is to turn that string into a palindrome.
Okay.
But Shri T, you can only add characters at the very beginning.
And of course, we're all about efficiency here.
Right.
So the challenge is to find the shortest possible palindrome you can create.
Right, so we can't just go adding the entire reverse string to the front every time.
Definitely not.
That would be too easy.
Definitely not the most elegant solution.
No.
To illustrate, let's say our starting string is ABCD.
Okay.
It's not a palindrome yet,
Yeah.
but what's the shortest way to make it one by adding characters only at the beginning?
Okay, let me think.
Yeah.
To make it a palindrome, we need to make sure it reads the same backward as it does forward.
Mm-hmm.
I'd say the shortest palindrome we can make is DCBAB-CD. We just need to add DCB to the front.
You got it. That's the kind of string manipulation we're aiming for.
Okay.
Now, how would you go about solving this programmatically? What's the first approach that comes to mind?
Well, whenever I encounter a problem like this, my initial instinct is to think about the most straightforward, brute force approach.
Right.
Even if it's not the most efficient, it can be a good starting point to understand the logic.
That's a great strategy.
Yeah.
Sometimes seeing the simplest solution helps highlight why more sophisticated algorithms are needed.
Yeah.
So walk me through how you'd solve this using brute force.
Okay, so with brute force, I'd probably start by reversing the original string.
Okay.
So in our EBCD example, the reverse would be DCB.
All right, what would you do next? Remember, we're looking for the shortest palindrome we can create by adding to the front.
All right, so after reversing the string, I'd start comparing prefixes of the original string to suffixes of the reverse string.
Okay.
So I'd check if A matches A, then AB matches B, and so on.
And somewhere in there you'd find the longest prefix that's also a palindrome.
Exactly. In our EBCD example, the longest palindromic prefix is just A.
Right.
Then I'd take whatever's left of the reverse string, which is DCB, and stick it onto the front of the original ABCD, giving us our shortest palindrome, DCBAB-CD.
You nailed the brute force approach.
All right.
It's conceptually simple, but as the name suggests, it has some drawbacks.
I have a feeling it's not going to win any efficiency awards, is it?
Not exactly.
Okay.
The brute force method involves a lot of comparisons, especially as the string gets longer.
Yeah.
You're essentially checking every possible prefix against every possible suffix, which can be computationally expensive.
So while it's easy to understand, it could get pretty slow for really long strings.
Precisely. Imagine dealing with strings containing thousands or even millions of characters, like DNA sequences or large text data sets.
Oh.
The brute force method just wouldn't cut it.
That makes sense.
Yeah.
So before we explore more efficient methods,
Sure.
are there any common pitfalls people might encounter with this brute force approach, or any questions they might have about the problem itself?
Absolutely.
Okay.
One common mistake is not correctly identifying the longest palindromic prefix. You need to make sure you keep checking prefixes until you find the absolute longest one to guarantee you're creating the shortest possible palindrome.
That's a good point. It's easy to stop prematurely and end up with a longer palindrome than necessary.
Right.
Any other gotchas to watch out for?
Another important thing to remember is that we're only allowed to add characters at the beginning of the string.
Right.
It's a specific constraint of this problem.
Yeah.
If we were allowed to add characters anywhere, it would be a whole different ballgame.
Right. That limitation is what makes this problem unique and, well, a bit more challenging.
Exactly.
So we've got our brute force method down.
Yeah.
It works, but it's not the most efficient.
Right.
What's another approach we could consider that might be a bit more clever?
Well, let's think about how we can improve upon the brute force method.
Yeah.
Instead of comparing every single prefix and suffix, what if we could strategically shrink the problem space?
Okay. I like where you're going with this.
Yeah.
How do we shrink the problem space when it comes to strings and palindromes?
One approach is to use 2 pointers and a touch of recursion.
Okay.
Imagine you have one pointer starting at the beginning of the string and another at the end.
So for our example, string ABCD, one pointer would be on A and the other on D.
Exactly. Now you move these pointers inward, comparing the characters they point to at each step.
Okay.
If the characters match, both pointers move one step closer to the middle.
I see what you're getting at. As long as the characters match, we're essentially confirming a potential palindromic prefix, right? It's like we're shrinking the problem from both ends.
You've got it. And this process continues until we either hit a point where the characters don't match or the pointers meet in the middle.
Okay, that makes sense.
Yeah.
So what happens if the pointers don't match? Let's say our string was abikbabkaba instead.
Perfect example. Let's walk through it. Initially, both pointers would point to A, which is a match. They move inward to B, and B, another match. This continues until the left pointer is on C, and the right pointer is on B, no match.
Right. So we've confirmed that abo abke is a potential palindrome, but we still have the remaining ba to deal with.
Exactly. And this is where recursion comes in. We can break the problem down by recursively calling the shortest palindrome function on that remaining substring ba.
So we're essentially saying, okay, we know abikbe is good so far, but let's figure out the shortest palindrome we can make with this leftover ba and then combine the results.
Precisely. And in this case, the shortest palindrome for ba is simply aba. We can then combine that with the abas ba we already know as palindrome.
So to put it all together, we'd reverse that remaining bar to get ab appended to aba, giving us ababa, and finally prepend that to the original abis, resulting in abakabkaba as the shortest palindrome.
That's exactly right. We've effectively broken down the problem into smaller, self-similar pieces, solved them recursively, and then combined the solutions.
This two-pointer approach is definitely more elegant than brute force. We're strategically shrinking the problem space and avoiding unnecessary comparisons. But is it the most efficient solution possible? Is there any room for improvement? It seems like we've made some good progress moving from a brute force approach to a more elegant two-pointer solution.
Yeah.
But I'm always curious to see if we can push the boundaries of efficiency even further.
Right.
Is there another way to solve this problem that's even more optimized?
You're thinking like a true coder.
Yeah.
There's always room for optimization. And when it comes to string manipulation, there's one algorithm that often steals the show. The Knuth-Morris-Pratt algorithm, or KMP for short.
KMP. That sounds pretty intense.
It's a mouthful.
What's so special about this algorithm, and how does it relate to finding the shortest palindrome?
KMP is a pattern matching algorithm that's all about finding occurrences of a pattern within a larger string.
Okay.
And it does so with remarkable efficiency. Now, you might be thinking, but we're not exactly searching for a specific pattern. We're trying to create a palindrome.
Right.
Here's the key insight. We can transform our problem into a pattern matching task.
Okay, I'm intrigued. How do we connect palindromes to patterns?
Remember how in the two-pointer approach we were looking for the longest palindromic prefix? Well, we can cleverly modify our string to make this task equivalent to finding the longest prefix that's also a suffix in this modified string. And guess what? KMP excels at exactly that.
I see where you're going with this. So how do we modify the string to make this work?
It's quite simple, actually. We create a new string by concatenating the original string with its reverse, but we separate them with a special character, like a hashtag.
So if our original string is ABCD, our modified string would become ABCD dtag DCBA.
Precisely. Now we apply the KMP algorithm to this modified string to generate what's called a failure function.
Okay, a failure function sounds a bit ominous. What does this function actually tell us?
Think of it like a roadmap for navigating mismatches.
Okay.
Imagine you're trying to find the word CA in a long sentence.
Wow.
You've successfully matched CA, but the next letter isn't a T. A naive algorithm would start the search all over again from the beginning.
That sounds pretty inefficient, especially if the sentence is really long.
Exactly. But KMP is smarter than that. The failure function tells you, based on the pattern you're searching for, how far you can shift your search forward without missing a potential match.
So it helps us avoid unnecessary comparisons and makes the search much faster. I'm starting to see how this could be powerful. But how does this failure function relate to finding the shortest palindrome in our modified string?
The magic lies in the last element of the failure function. It tells us the length of the longest suffix of our modified string that also matches a prefix. And this, my friend, corresponds directly to the longest palindromic prefix of our original string.
Wow, that's pretty clever. So in our ABCTT ABCD example, the KMP algorithm would tell us that the longest palindromic prefix of ABCD is just A, since that's the only part that matches at both the beginning and the end of the modified string.
Exactly. The failure function would give us a length of 1, indicating that the longest palindromic prefix is just 1 character long.
So then we just simply take the remaining DCB from the reversed part of our modified string and add it to the front of ABCD to create the shortest palindrome DCBABCD.
You got it. And the beauty of KMP is that it accomplishes all of this with remarkable efficiency. It has a time complexity of ON, meaning the time it takes scales linearly with the length of the string. No matter how long the string gets, the time it takes to find the shortest palindrome grows proportionally.
That's a huge improvement over the O in complexity. Ultimate winner when it comes to solving the shortest palindrome problem.
It's definitely the most efficient solution in terms of time complexity. But as with any algorithm, there are trade-offs.
Right.
KMP requires a deeper understanding to implement correctly, particularly when it comes to constructing and interpreting that failure function.
Right. That part still seems a bit mysterious to me.
Yeah.
But I guess the payoff in efficiency can be well worth the effort, especially when dealing with really massive data sets.
Absolutely. Think about bioinformatics, where scientists are working with DNA sequences that can be billions of characters long. Or imagine optimizing search algorithms for huge text databases. In these scenarios, using an algorithm like KMP could be the difference between a solution that takes hours or even days and one that takes mere seconds.
That's incredible. It's amazing how the right algorithm can make such a dramatic impact.
It really highlights the importance of understanding different algorithmic approaches and choosing the right tool for the job.
Well, this has been an incredible deep dive into the shortest palindrome problem. We've gone from a simple brute force approach to a more elegant two-pointer solution, and finally arrived at the efficiency powerhouse that is KMP.
It's been quite a journey.
And along the way, we've seen how even a seemingly straightforward problem can have hidden depths and opportunities for optimization.
For sure.
Exactly. And for all of you listening out there, I encourage you to keep exploring, keep learning, and never be afraid to experiment with different algorithms. You never know when that knowledge might come in handy. Until next time on AI.Code.Cast.